Welcome to this coding walkthrough. Today, we'll explore LeetCode problem number 1713, minimum operations to make a subsequence. This problem challenges us to minimize the number of insertions required to transform one sequence into a subsequence of another, testing our understanding of dynamic programming and data structures. Let's dive in. The problem asks us to determine the minimum number of operations required to make one array, called target, a subsequence of another array, called ARR. Here's how this works. In a single operation, you can insert any integer at any position in ARR. For example, if ARR is 1, 4, 1, 2, and you insert 3 at index 2, the new array becomes 1, 4, 3, 1, 2. A subsequence is simply a sequence derived from an array by deleting some elements without changing the order of the remaining elements. For instance, 2, 3, 6 is a subsequence of 1, 2, 3, 4, 5, 6, because the relative order of 2, 3, and 6 is preserved. The input consists of two arrays, target and ARR, both with constraints on their length and element values. The goal is to return the minimum number of insertions needed to make target a subsequence of ARR. Let's consider an example to understand the problem better. Suppose target is 5, 1, 3, and ARR is 9, 4, 2, 3, 4. The output in this case is 2. Why? Because we want target to become a subsequence of ARR, meaning all elements of target must appear in ARR in the same order. The issue here is that 5 and 1 are missing from ARR. To fix this, we can insert 5 and 1 into ARR. For example, after inserting these elements, ARR could look like 5, 1, 9, 4, 2, 3, 4. Now, target equals 5, 1, 3 appears as a subsequence. The total number of insertions required is 2 in this case. Now let's look at another example. Here, target is 6, 4, 8, 1, 3, 2, and ARR is 4, 7, 6, 2, 3, 8, 6, 1. The output is 3. To make target a subsequence of ARR, we need to insert 3 elements, 4, 8, and 2. For instance, we could insert 4 and 8 near the start of ARR, and 2 towards the end, resulting in an ARR like 6, 4, 8, 7, 6, 2, 3, 8, 6, 1, 3, 2. Notice that after these insertions, target equals 6, 4, 8, 1, 3, 2 is now a subsequence of ARR. In total, 3 operations are required to achieve this. Finally, let's discuss some constraints and edge cases. First, the lengths of target and ARR can go up to 100,000, and their elements can be as large as 1 billion. The integers in target are guaranteed to be distinct. Now, consider an edge case where ARR is empty but target is not. Here, every element of target must be inserted into ARR, so the result is simply the length of target. On the other hand, if ARR already contains all elements of target in the correct order, no insertions are needed, and the result is 0. For large inputs, the solution must be efficient, ideally running in O, n log n, time, as naive approaches would be too slow for these constraints. To tackle the problem of determining the minimum operations required to make ARR a subsequence of target, we can start by exploring different approaches. One intuitive but highly inefficient strategy would be the brute force approach. The idea here is straightforward. We generate all possible subsequences of ARR and check which ones align with target. If certain elements from target are missing in ARR, we count those as insertions. While this approach is conceptually simple, it's practically infeasible because the number of subsequences grows exponentially with the size of ARR. The time complexity of O2 to the power of n makes this approach unsuitable for large inputs, so it is quickly dismissed in favor of more efficient solutions. This leads us to consider optimized strategies, particularly those leveraging the properties of subsequences. A more efficient strategy is based on the concept of the longest increasing subsequence, or LIS. The key insight here is that if we can map the elements of ARR to their order in target, the problem transforms into finding the LIS of the resulting sequence. The length of this LIS represents the maximum subsequence of ARR that aligns with target. From there, the number of insertions required is simply the difference between the size of target and the length of the LIS. To implement this, we first create a mapping of target elements to their indices for quick lookups. Then, we transform ARR into a sequence of indices based on this mapping, filtering out any elements not in target. Finally, we compute the LIS of the transformed sequence using a binary search approach, which is both efficient and scalable. This solution ensures that we achieve an optimal balance between accuracy and performance. The crucial realization that drives this solution is that the problem fundamentally reduces to finding the LIS in the mapped version of ARR. This allows us to leverage efficient algorithms, such as binary search, to solve the problem in O and log n time. This is a massive improvement over the brute force approach, making it feasible for much larger inputs. The use of binary search ensures scalability, while the mapping and LIS-based method provides an elegant and structured solution. However, there are trade-offs to consider. While the pre-processing step of mapping target to indices is necessary for this approach, it adds a layer of complexity compared to simpler methods. Dynamic programming could also be used to compute the LIS, but at O n squared complexity, it is less efficient than the binary search alternative. Ultimately, the LIS with binary search approach is chosen because it provides the best combination of clarity and efficiency for solving this problem. By reducing this problem to the well-known LIS subproblem and leveraging efficient algorithms and data structures, we achieve both optimal performance and scalability. This approach highlights the power of transforming complex problems into simpler, more familiar ones. With the combination of quick preprocessing, efficient computation, and the use of binary search, we not only solve the problem effectively but also gain a deeper understanding of how to apply advanced techniques to real-world scenarios. This strategy demonstrates the importance of breaking down a problem into its core components and choosing the right tools to address each part efficiently. In this problem, we are tasked with transforming one array, RR, to make it a subsequence of another array, target. A subsequence means that the elements must maintain the same relative order as in the original array, but they don't have to be contiguous. To achieve this, we need to determine the minimum number of insertions required to modify ARR so it matches the subsequence structure of target. Our approach starts by mapping the elements of target to their indices. This creates a reference that allows us to efficiently determine how elements in ARR correspond to target. For instance, if target is 5, 1, 3, we create a dictionary where each value in target is mapped to its index, resulting in 5 o'clock, 1, 1, 3, 2. Once this map is ready, we then filter ARR by replacing its elements with their corresponding indices from the map, ignoring any elements of ARR that are not in target. For example, if ARR is 9, 4, 5, 1, 23, using our map, we transform it into 0, 1, 2, which represents how its elements align with target. Once we have the filtered sequence of indices, we move to the next step, finding the longest increasing subsequence, or LIS. This is crucial because the LIS represents the largest portion of ARR that already maintains the relative order defined by target. By maximizing this subsequence, we minimize the number of insertions required. We use a binary search-based LIS algorithm to efficiently find this subsequence. For example, if the filtered sequence is 0, 1, 2, the LIS is 0, 1, 2, which has a length of 3. Finally, we calculate the minimum number of operations by subtracting the length of the LIS from the length of target. The formula is min_operations equals len, target, len, LIS. For instance, if target has 3 elements and the LIS is also of length 3, then no insertions are needed because RR already contains a valid subsequence of target. However, if the LIS is shorter, insertions will be required to fill the gaps. To understand why this approach works, it's important to note that a subsequence is different from a subset. It must preserve the relative order of elements. This is why we rely on the LIS algorithm to identify the longest portion of ARR that aligns with the order in target. The mapping and filtering steps are efficient due to the use of a dictionary, which allows us to look up indices in constant time, making the filtering process linear with respect to the size of ARR. Additionally, the LIS algorithm is implemented using binary search, which ensures a time complexity of O n log n. This combination of efficient mapping and filtering, followed by the optimized LIS computation, makes our solution scalable to handle large inputs, such as arrays with 10,000 elements. By leveraging key data structures like dictionaries for mapping and lists for the filtered sequence, we ensure every step is both intuitive and efficient. To further optimize the solution, we use the bisect_left function for binary search when implementing the LIS algorithm. This ensures that we find the appropriate position for each element in the LIS list with minimal overhead. Additionally, we can handle edge cases efficiently. For instance, if ARR is empty, all elements of target must be inserted, resulting in len target operations. Conversely, if target is empty, no operations are needed since there's nothing to match. If ARR already contains all elements of target in the correct order, no operations are required. Finally, if there are no common elements between ARR and target, we must insert all elements of target. These considerations ensure our solution is robust and handles all scenarios, from the simplest cases to the most complex edge cases. This implementation solves the problem of determining the minimum number of operations required to make ARR a subsequence of target using an efficient approach based on the longest increasing subsequence, LIS. Step-by-step explanation. Step 1. Map target elements to indices. We start by creating a mapping of each value in target to its corresponding index using a dictionary. This allows us to efficiently look up the position of any value in target, which is critical for the subsequent steps. For example, if target equals 5, 1, 3, the map will be 5 o'clock, 1, 1, 3, 2. Step 2. Extract relevant indices from ARR. We iterate through ARR and build a list indices that consists of the indices of elements in ARR that also exist in target. Each element in ARR is checked against the target_index_map to determine if it is part of target. If it is, its index in target is appended to indices. For instance, if ARR equals 9, 5, 3, 1, the resulting indices could be 0, 2, 1, because 5, 3, and 1 exist in target. Step 3. Compute the longest increasing subsequence, LIS. The core of the solution is finding the LIS of the indices list. This step determines the maximum number of elements in ARR that can appear in the same order as in target. We use the bisect_left function to perform this efficiently. For each index in indices, if it can extend the LIS, i.e., it is greater than the current largest element in the LIS, we append it. Otherwise, we replace the smallest element in the LIS that is greater than or equal to the current index to maintain the LIS property. Step 4. Calculate minimum operations. Finally, the number of operations required to make ARR a subsequence of target is determined by subtracting the length of the LIS from the total length of target. This is because the elements already part of the LIS do not require any insertion. Complexity analysis *. Constructing the target_index_map takes O(n), where n is the length of target. Iterating through ARR to build the indices list takes O(m), where m is the length of ARR. Computing the LIS takes O(k log k), where k is the length of indices. Thus, the overall time complexity is O(n plus m plus k log k), which is efficient for the given constraints. This approach ensures correctness and efficiency while handling all edge cases, such as when ARR contains no elements from target or when ARR already matches target fully. Here, we begin by mapping each value in the target array to its corresponding index using a hash map. This helps us quickly look up the position of any value in target. Next, we iterate through the ARR array and check if each value exists in the target. If it does, we retrieve its index from the map and add it to a list called indices. This list now represents the sequence of indices in target that correspond to the elements of ARR. The goal is to find the longest subsequence in this list that maintains its order, which will help us determine the minimum operations needed. To do this, we calculate the longest increasing subsequence, or LIS, of the indices list. We initialize an empty list called LIS to keep track of the increasing subsequence. For each index in indices, we use a binary search to find its position in LIS. If the index is larger than all elements in LIS, we add it to the end. Otherwise, we replace the appropriate element to maintain the order. Finally, after constructing the LIS, we calculate the minimum operations required. This is simply the difference between the length of the target array and the size of the LIS. The helper method binary search is used to efficiently find the position where a given index should be inserted or replaced in LIS. It performs a standard binary search, adjusting the left and right bounds until the correct position is found. This approach ensures that we can maintain the LIS in O log n time for each insertion, resulting in an overall time complexity of O n log n for the LIS calculation. By combining these steps, we efficiently determine how many elements need to be added or removed to make target a subsequence of ARR. Here, we are working through a basic example. The target array is 5, 1, 3, and the ARR array is 9, 4, 2, 3, 4. The first step is to create a mapping of the indices of elements in the target array. This gives us a dictionary where each value in target is mapped to its index, 5 o'clock, 1, 1, 3, 2. Next, we process the ARR array to extract the indices of elements that also exist in target. Starting with an empty indices list, we iterate through ARR. If an element in ARR exists in the target_index_map, we append its corresponding index to indices. For example, 3 exists in target at index 2, so we add 2 to indices. Elements like 9, 4, and 2 are not in target, so they are skipped. By the end of this step, the indices list contains only 2. Now, we have the resulting indices list as 2. The next step is to find the longest increasing subsequence, or LIS, of this list. Using binary search, we process each value in indices to construct the LIS. For the value 2, we insert it into our LIS list, resulting in LIS equals 2. The length of this LIS is 1. Once we have the LIS, we can calculate the minimum number of operations needed to make target a subsequence of ARR. This is done by subtracting the length of the LIS from the length of the target. Here, len, target, is 3, and len, LIS, is 1, so the result is 3 1 equals 2. This means we need 2 operations to achieve the goal. In this second example, the target array is 6, 4, 8, 1, 3, 2, and the ARR array is 4, 6, 8, 3, 2. Following the same approach, we create the target_index_map by mapping each value in target to its index, 6 o'clock, 4, 1, 8, 2, 1, 3, 3, 4, 2, 5. Then, we process the ARR array to extract the indices of elements that are also in target. Starting with an empty indices list, we check each value of ARR. For example, 4 is in target at index 1, so we append 1 to indices. Similarly, 6 corresponds to index 0, 8 to index 2, 3 to index 4, and 2 to index 5. By the end of this step, the indices list becomes 1, 0, 2, 4, 5. With the indices list now at 1, 0, 2, 4, 5, the next step is to find the LIS. Using binary search, we process each value to build the LIS. First, we insert 1, resulting in LIS equals 1. Then, 0 replaces 1 as it is smaller, making LIS equals 0. Next, 2 is appended to LIS, giving LIS equals 0, 2. Similarly, 4 is appended to get LIS equals 0, 2, 4, and finally, 5 is appended, resulting in LIS equals 0, 2, 4, 5. The length of this LIS is 4. To calculate the minimum operations, we subtract the length of the LIS from the length of target. Here, len, target, is 6, and len, LIS, is 4, so the result is 6, 4 equals 2. This means 2 operations are needed. After calculating the LIS length, we determine the minimum number of operations required. For this example, the length of the target array is 6, while the LIS length is 4. Subtracting these gives a result of 6, 4 equals 2, which means 2 operations are necessary to make the target array a subsequence of ARR. Now, let's consider a final example where there are no matching elements between the 2 arrays. In this last example, the target array is 1, 2, 3, and the ARR array is 4, 5, 6. First, we create the target_index_map as 1 o'clock, 2, 1, 3, 2. Then, we process the ARR array to extract indices. Here, none of the elements in ARR are present in target, so the resulting indices list remains empty. Since the indices list is empty, there is no LIS to compute, and its length is 0. To calculate the minimum operations, we subtract the length of the LIS from the length of target. With len, target, as 3 and len, LIS, as 0, the result is 3, 0 equals 3. This means all 3 elements of target need to be added, as no subsequence currently exists. To analyze the time complexity, we begin with the step of mapping target values to their indices. Here, we iterate through the target array, which has n elements, to create a dictionary called target_index_map. Each value in target is mapped to its index, and since this is a single pass through the array, this step takes n time. Next, we build the indices list by iterating through the ARR array, which has m elements. For each value in ARR, we perform a dictionary lookup in target_index_map. Since dictionary lookups have a constant time complexity of 1, this entire step takes m time. Together, these two steps lay the groundwork for the main algorithm while maintaining efficiency. The next step is finding the longest increasing subsequence, or LIS, in the indices list. This is done with a greedy algorithm paired with binary search. As we iterate through the indices list, which has at most m elements, we use the bisect_left function to determine where the current value should be placed in the LIS sequence. The binary search operation within the LIS array takes log k, where k is the current length of the LIS. In the worst case, we process all m elements, resulting in a time complexity of m*log k. Since the LIS size k can grow to at most min n m, the complexity becomes m*log min n m. Finally, calculating the minimum operations is a simple subtraction with a time complexity of 1. Combining all steps, the overall time complexity is n plus m *log min n m. For large inputs, the LIS computation dominates, making the effective complexity m*log min n m. Now, let's discuss space complexity. The first step involves creating the target_index_map dictionary, which stores n key-value pairs, requiring n space. The second step involves building the indices list, which holds at most m values, corresponding to the elements in ARR that are also in target. This step contributes m space. Lastly, the LIS computation dynamically maintains a list to store the sequence, which can grow up to a size of min n m. This adds min n m to the space complexity. When we combine these components, the overall space complexity becomes n plus m, which is linear and manageable given the constraints. Let's compare this optimized approach to the brute force method. A naive solution would involve generating all possible subsequences of ARR and checking each one against target. Generating all subsequences of ARR requires 2 to the power of m time, and for each subsequence, verifying it against target takes n. This results in an overall complexity of n*2 to the power of m, which is prohibitively expensive for large inputs. By contrast, the optimized solution transforms the problem into finding the LIS of mapped indices, significantly reducing the time complexity to m*log min n m. This drastic improvement is supported by a mathematical breakdown of each operation's contribution, where the LIS step dominates. Similarly, space usage is reduced to linear components, including the dictionary, indices list, and LIS array, making the solution both time and space efficient. Finally, let's consider the best, worst, and average cases for the algorithm. In the best case, all elements of ARR are present in target and are already in increasing order. Here, the LIS step only appends to the end of the sequence, minimizing binary search operations. This results in a time complexity of n plus m. In the worst case, all elements of ARR are in target but in reverse order, requiring the LIS step to perform binary search over the entire sequence for each element. This leads to the maximum time complexity of m*log min n m. On average, the algorithm's performance remains dominated by the LIS computation, maintaining a time complexity of m*log min n m. These cases illustrate the algorithm's efficiency across various scenarios, ensuring robust performance even for large inputs. When tackling this problem, there are several common pitfalls to watch out for. First, misunderstanding the problem requirements is a frequent issue. Some mistakenly believe the task involves directly modifying the target array, rather than making ARR a subsequence of target. This misunderstanding can lead to completely incorrect approaches. Instead, your focus should always be on aligning ARR with target. Another common mistake is attempting a brute force subsequence check. Generating all possible subsequences of ARR leads to exponential time complexity, which is infeasible for larger inputs. Instead, you should aim for optimized solutions like dynamic programming or advanced data structures. Additionally, failing to recognize the importance of indices in target can prevent you from using efficient algorithms like longest increasing subsequence (LIS). To avoid this, pre-process target into a dictionary for quick index lookups. It's also critical to handle duplicate values properly. If ARR contains values that don't exist in target, those should be filtered out before constructing the LIS. Including unnecessary values can lead to incorrect results or unnecessarily high complexity. Lastly, don't overlook edge cases, such as when ARR or target is empty, when ARR is already a perfect subsequence of target, or when there are no common elements between the two arrays. Testing these scenarios ensures your solution is robust and comprehensive. Now, let's focus on key takeaways that are particularly valuable in an interview setting. A critical insight here is recognizing that the problem can be reduced to finding the longest increasing subsequence of ORR after mapping its values to the indices of target. This transformation is the foundation of the optimal approach. To achieve this, you should use a combination of a hash map for mapping target values to indices, and binary search for efficiently computing the LIS. This results in an O, n log n solution, which is highly efficient and scales well for input sizes up to 10,000. It's also important to discuss trade-offs. For example, while dynamic programming can solve the problem in O, n squared, it becomes inefficient as the input size grows. On the other hand, brute force approaches like checking all subsequences are entirely impractical due to their exponential time complexity. Demonstrating an understanding of these trade-offs showcases your grasp of algorithmic efficiency. Additionally, proactively addressing edge cases, such as empty inputs or disjoint sets, highlights your thoroughness and attention to detail. Lastly, when explaining your solution, emphasize how pre-processing target and applying binary search reduces complexity. Doing so not only strengthens your explanation but also impresses interviewers with your ability to optimize and communicate effectively. Finally, let's explore some related problems and alternative approaches. For related problems, LeetCode 300, longest increasing subsequence, is particularly relevant since it introduces the core concept used in this problem. Similarly, LeetCode 792, number of matching subsequences, involves efficient subsequence checking techniques. LeetCode 1187, make array strictly increasing, also requires array transformations and incorporates LIS-like ideas. Lastly, LeetCode 354, Russian doll envelopes, is a classic problem that combines sorting with LIS for optimization. In terms of alternative approaches, dynamic programming is a straightforward method with O, n squared, complexity. While it's less efficient for large inputs, it can simplify implementation for smaller scale problems. The optimal approach, however, uses binary search with pre-processing, achieving O, n log n. This involves mapping ARR to target indices and then solving LIS efficiently, making it the best choice for scalability and interviews. Another option is combining hashing with sorting, which can simplify subsequence checks in certain variations of the problem. However, this approach might increase implementation complexity without necessarily improving runtime. By being aware of these alternatives and their trade-offs, you can adapt your solution strategy based on the specific constraints and requirements of the problem at hand. Great job! To wrap up, we've covered an efficient approach to solve this challenging problem using dynamic programming and binary search. Remember, mastering these concepts will significantly enhance your problem-solving skills. Thank you for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!